Hey, okay, welcome to our next thermodynamics lab. This is the one that I had mentioned on my Sunday email about we're going to do some thermal conductivity. We're going to do 5 different materials, actually, and the equipment here in front of you I have warming up. In a normal face-to-face setting, you would only have one and you would swap it out, but given that I had a bunch to work with and I thought watching me swap them out would have been boring on video, I decided to run this experiment today with you. Of course, we're lab partners, but we're just going to make all 5 of them go at the same time. So that probably is going to save quite a bit of time. So I'm anticipating this might be a shorter video compared to some of the other labs. But on the other time, let me point out, you're kind of a guinea pig here. We've never done this one. As I also said in my Sunday email, we had an old thermal conductivity that we never really liked it. Well, we liked it 30 years ago, but since then it had issues and problems and just needed to be upgraded and replaced. So that's what this is. So we've got some new equipment and we've never used it before, and so I'm kind of excited to see what kind of results I get. And I've got them warming up. In fact, they're already warming and actually going. I'll explain them in just a second. But let's talk about the theory. Let's come over here to the whiteboard. Excuse me. And let me put on the whiteboard here the equation for a one-dimensional thermal conductivity that you've been working with in your homework. And here it is. Let's talk about these symbols. Here's what it says. It says that if you have a temperature gradient, so in other words, if you have one side of a material, and let me try to draw the material we're going to be using. We're going to have a plate of material. In fact, I'll just show you one of them. Here's one of the ones we will be using. This is a glass plate. How about I grab a wood plate? Now it does have a aluminum coating on it, but I hope you can kind of see on the side it's wood. And so I got wood, I got glass. Excuse me. I also got some sheetrock. But I'll talk about the materials in a second here. But if you could imagine this little rectangular solid here, and on one side of it we get it really hot, and so on the bottom side we're going to boil water and get it at 100 degrees Celsius, and then on the top side we're going to put a cylinder of ice, and so that's going to be 0 degrees. In fact, let me kind of show you your equipment. So here is the apparatus. You can kind of see this one's got the glass plate already mounted on it. And so here it is. And what I'm going to do is put hot steam into this hole. And so underneath the glass plate is going to be 100 degrees. So that's this part here that I'm talking about. And then what's going to happen is heat energy is going to transfer up from underneath through the glass into the ice. And so I'll put some ice on top, and our ice will look something like this. Here's one of our frozen pieces of ice. And so here's this cylinder. It's a little plastic container, but we're just going to put this plastic container of ice right on there. And then it's going to melt. And as you can hopefully see, there is a little channel for the water to run down and drip in a container. And so the heat that conducts through whatever material we're using, and we'll do glass first, goes and melts the ice. And of course, how quickly does it melt the ice is telling us how quickly the heat is transferring through. See, and that's what we're going to be looking for. Let me come back to this equation. So the temperature gradient, that is the temperature difference per thickness, is right here. So if I rewrite this equation as delta T, then this right here is going to be 100 degrees Celsius. That's going to be the temperature difference between the bottom of the glass and the top of the glass. Now, the thickness, let me just write it as delta X for now. But in a few moments, when we're done talking about theory, I'll actually go ahead and measure this. Whoops, put my ice back. I'll go ahead and measure this thickness. And so that's one of the many things we'll need to record. Now, the other thing here, this A for area, is then what is the area of this chunk of ice? And so as the heat conducts from the bottom side, we're going to say it's kind of channeled in a cylinder. And I suppose that's not completely 100% true. Heat would actually come from a slightly bigger area and funnel into my cylinder. But that's this whole idea. And in fact, I'll even show it to you, again. So here's the square and here's the cylinder on top. So again, imagine the heat underneath. Because once we hook it up, it's kind of hard to see that there is heat under there. And of course, here's the main point of the lab, is to find this right here. This is the thermal conductivity of that material. And so we're going to be working with 5 different materials. So we will measure this, and we will also measure this over here. Now I'll put absolute value so I can get rid of the negative sign. But I'm also going to do this. I am going to say that the heat that flows from the hot steam and melts the ice, all of that goes to melt the ice. So I'm going to write this as M and L sub F. The M is the mass of the ice that melted, and the LF is the latent heat of fusion. Now I will then rewrite that as LF dm dt, then the K, then the A, then the delta T, and the delta X. All right, so let me say again, our experiment here today is to learn a little bit more about thermal conductivity. Is this boiling too much, or filling it up kind of quick?
Yeah.
All right, maybe I'll move it over to a different one for right now, and we'll figure that all out in a minute. We'll just make a mess here. All right, but with that in mind, let me come back over to here and point out, and you can see our stuff is now very warm and ready to go. But we're going to do this. We're going to measure everything in this equation. So let me put a box around it. Except, of course, for the K. And that's what you're going to calculate. What is the thermal conductivity of? And like I said, there's 5 materials. So I've mentioned one of them so far, and that is right here. That the temperature difference is going to be 100 degrees. Now, what about its thickness? What about its area? What about the latent heat of fusion? And then what about the rate at which the ice is melting? Well, let me start with some easier ones as we get started here collecting our data. As I said, the setup alone will guarantee that that's 100 degrees. The area, and so let me just put it right here, area would be pi r squared. And why don't I just measure the radius with you? And so this will be our first measurement. I've got the little ruler right here. And we've got a bunch of cylinders right there. They're already actually on there, but this is an identical one. So I'm going to measure the diameter and cut it in half of this one. And so this is 8 centimeters, which makes 4 centimeters for its radius. And I'll just put pi times 0.04 meters and square it. And I'll leave that job for you to get out your calculator and calculate that area. All right, so those are the two easy ones, the temperature difference and the area. Another easy one, let me come to this side of the equation, is the latent heat of fusion of ice. That is the 333 joules in order to melt 1 gram. Okay, so let's see. So we know that. Now we know that, and we know that. The harder ones are these. So let's measure their thickness. And then once we measure the thickness, let's go ahead and run what I'll call the meat of the experiment and figure out at what rate is the ice melting. And so we'll set a little timer, we'll set it for 5 minutes, and we'll just see how much ice melts during a 5-minute period. Okay, so with that being said, let me jump on to this one. Now all of our materials are slightly different, and so let me find that glass piece again. Here's the glass piece. Let me get out some calipers. Let me walk over here to our table, because here's what we're going to be filling in. And so this is going to be your assignment. This is going to be your lab. And maybe the good thing about being a new one and a guinea pig is I'm not going to have any discussion questions. I just want you to fill out this table and turn it in. That's going to be your whole assignment for the lab. And maybe next year then I'll put it in the lab manual, but you won't find it in the lab manual. Well, excuse me, what you will find if you look up thermal conductivity is the old equipment. So don't look at that. If you look at that, it's not going to make any sense to what you're seeing right here on this video. Okay, that's the old equipment. So don't look in the lab manual. All you want to do is make a table like this with all the details figured out. And this gives me a chance then to point out what are the 5 materials we're going to be using. So the first material is glass, then we'll go to plastic, then we'll go to sheetrock, then we'll go to masonite, and then we'll go to wood. And I'll show you the materials here before we get started, but here's the glass piece. And so let's look here at some different parameters I have wrote down in the table. And starting with glass, I'm going to put here, okay, the temperature difference is 100 degrees Celsius. And the thickness that the heat has to go through is 5.88 millimeters. So if I put it in meters, it's 0.00588. Okay, so I've got the temperature difference, I've got the thickness. Now, once we get started, you'll see what these other columns are for. But again, let me move on to the other materials. All right, so let me grab a plastic piece. So here's a plastic piece. Let me come over here and do the same thing. So with the plastic, there's going to be 100 degrees difference. And it's going to have a thickness of 561. So 5.61 millimeters. So let me change that into meters. Okay. Let me grab the third material. What do we have? Sheetrock. And sheetrock is drywall. There's stuff in your walls here. And so I'll hold this one up here. You can kind of see that chalky color in there that maybe you're used to if you've ever done any sheetrock or wall repairs. But we'll look at what rate does heat transfer through sheetrock. And our sheetrock has a thickness of 10.22 millimeters. 1, 2, 3. And so 0.01 1022 for a temperature difference of 100 degrees. All right, our fourth material is the masonite, which is kind of a hard artificial wood type material. Kind of a brown color. Now I've wrapped it in aluminum foil here so that it'll conduct the heat with the ice better, but the material itself is actually masonite. So let me come over here and do the same thing with the masonite that I've done with the other materials and measure its thickness. And I think I need to re-zero that. Okay. There we go. 586. 586. 0, 0. And again, the way we're hooking it up with our boiling water, we're going to have a temperature difference of 100. And then finally, we've just got some pine. It's actually a laminated pine. I don't know if that matters. But here is our 3 layers of pine. And let me just re-zero that. There we go. And so this is just a little bit thicker. Looks like this is a 648 0 0. Okay, and that too is going to be set up at 100 degrees. Oh good, this stuff's going real well. All right, well now I think we're actually ready to begin the experiment. Let's take a look at the equipment. Ron, I don't know how much you've been able to show the students. Maybe I'll just focus on one of them. Come over here to the glass one. Here's this idea all put together. So I've got the little steamer right here, and so I got boiling water going through this pipe right here, and it's really hot, and so it comes up underneath the glass plate on here. And then on top here, I have this big cylinder of ice. So I'll kind of lift it up so you can see this cylinder of ice. And so it's just melting the ice, and as it melts it gets collected in this beaker right here, and that's the idea. I just want to collect it in the beaker, and so I'll go ahead and maybe start them about a minute apart, and as I have them apart, we'll then just record in between. So of course the first thing I have to do is to find out, well, how much does the beaker itself weigh, so that when I weigh it afterwards I can get the increase. And that's what these first 3 columns are. And so if you look at this first column, it says what's the mass of the beaker, and then after 5 minutes we'll say what is the mass of the beaker with water in it, and then we'll subtract the 2 to figure out how much mass is melted, and then we'll put the time. Now I'm going to shoot for 5 minutes. If I need more time than that, I will, so I want to just be a little bit careful not to write anything down, but 5 minutes is 300 seconds, so I think we're just going to do every one for 300 seconds, and from that we can get, and I'll come back over here, this last piece of the equation, and that's this, the amount of mass per time. And so we'll see how many grams per second. So then when we multiply it by here, we will then have joules per second. And then we will know everything in this equation except for this K. And that's why then you are going to be asked, right here, the last part of this table, is this is what you need to do. You'll need to calculate this conductivity, the thermal conductivity of glass, plastic, sheetrock, masonite, and pine. Okay? And so that's your assignment. In fact, I'll even leave this difference alone, so I'm going to make you do the subtraction to get the mass of the water, and then divide that by time to get the rate. But I'll fill in this column, and this column, and then you can calculate that column, and from that get the ultimate step, which is to get the thermal conductivity. So like I said, this is new. It's new to me and Ron and everybody, and so I'm going to do actually the same calculations once this video is gone, because I've never done these. I don't know what the numbers come out to be, and so I'm kind of curious, and so this should be fun. That's the fun thing about, I guess, doing something new here. So, all right, so with that in mind, why don't I just go in order? I put a glass plate on here, and then a plastic plate here, and a sheetrock here, and a masonite here, and a pine over here. And so I'm going to go with the glass here first. So I'm going to come over here to the scale, and I'm going to put my beaker on here and say, okay, this is 209.6. So 209.6. So there's my empty beaker. Let's look at the empty one that's going to go on to the plastic. This one is 179.1. 179.1 for that one. Let me come to this one, and looks like I got some water on the bottom. It overflowed, so let me dry that off pretty good. And see what the mass is of this one. 215.6. So 215.6 is the mass of the beaker I'm going to use to collect for the sheetrock. Over here, for the masonite, let me put it on here. And this one starts off 215.3. Alrighty, and one last beaker, which I kind of swapped it out and started using it. Let's see, should I wipe it out, Ron, or should I just, yeah, I'm gonna, yeah, let me do this for a moment. This will be my waste collector. And let me just dry this one. And so the pine one is going to be 175.9. 175.9. Nice. Okay. So, with all of that in mind, let me grab a stopwatch here. I'll put down my marker. And I will swap out this, I call it the waste one, with the new one, and then start the watch at the same time. Let me just get at the edge and go, ready, go. Okay. So, that one, well, I'll just leave it there. And so I'm going to let that collect for 5 minutes. Meanwhile, I'm going to do the same thing over here. If I do them a minute apart, 2, 3, 4, 5, and I got to stop that at the same time. So maybe I should, and I got plenty of time. Yeah, I can do another watch, but I think I'll do that one on the 30-second mark. So don't let me forget that I'm going to be off. So you watch when I start it. All right, here we go. We're getting close to 1 minute mark. 55, 56, 57, 58, 59, 60. Nice. Okay. And this is the one that was dripping off that lower edge, so I want to make sure I catch it. All right, so there's the plastic one. Although, how much is it collecting? You know, I might just make a on the fly change to 6 minutes. We'd collect more water, might be a little more accurate, and I wouldn't have to worry about, yeah, I might do that. Anyways, I'll decide as I get close here. All right, so again, I'll swap this one out at the 2-minute mark. And this one's getting close. So a minute 55, 56, 57, 58, 59, 60. All right. And this one too is dripping off the inner edge. Make sure I collect it. Okay, good. So 0, 1, 2, 3, 4, 5. Oh no, it's gonna work out perfect. Okay. And they seem to be collecting okay. Just want to make sure they're getting in the beaker and kind of a steady rate. This glass conducts pretty good. It's really dripping compared to the other ones. All right, well, I'll start getting ready for minute 3 here and swap this one out. Got 15 more seconds. This is the masonite one. You can see it kind of dripping and kind of getting ready here. 55, 56, 57, 58, 59, 60, okay. Let's put that one right there and let that one start collecting. Good. And that one's going pretty good actually. Let's see. Yeah, not quite as fast as that glass though. That's interesting. See, that's the cool thing about doing this for the first time. It's like I can look at these different materials, and I'm already a little surprised here at the glass. The glass is just zipping along, and the plastic is really slow. Sheetrock's a little bit, seems a little faster. Anyways, I better get ready for the last swap out. We got 20 seconds here. All right, so we get to minute 4 here. We'll just kind of push this one out of the way and get it started. 55, 56, 57, 58, 59, and 60. Nice. Okay. Got them all collecting. And of course, because of that, the glass over here has been collecting for over 4 minutes. So we'll see if I can grab my calculator, and in between 1 minute, if I can get over and weigh them and write them down in the table. Well, so I guess I won't need my calculator yet. Actually, I won't need it all. I'm going to leave that to you to do the calculation. But gives me a whole minute to make sure it's dry and write it down and get an answer here. All right. So we're about coming up. We got about 10 more seconds left for the ice here. And out. Done. All right. Let me put the waste bucket there. All right. It's collecting. Let me dry it off. Let me now weigh it, and we are at 286.2. 286.2 grams. Nice. Huh? 300 seconds. And then the time was a perfect 300 seconds. Yes. Let me put that in. Good. And that only took me 40 seconds to write down, so that's good. So I can get ready now for the next one. Let me put my little stopwatch right here. I got about 12 seconds. And I will swap out now the plastic one. And 960, got it. All right, I'll put the waste one there. Yeah, there's hardly any water in here. That plastic one is a low thermal conductivity. So this is a 199.9. 199.9 in the same 300 seconds. All right, and that's perfect. It gets me ready for the next one here. Still got about 20 seconds more, and then we'll have completely captured 5 minutes worth of from the sheetrock. And it's interesting. I see the sheetrock conducts better than the plastic. I would not have guessed that. All right, 3 seconds. 2, 1, 0. Pull away and let the waste collect. All right, and let's see how much water we have collected, and then we can get the thermal conductivity. This is 231.7. So 231.7 during those same 300 seconds. Okay. And I'll put my stopwatch where I can kind of see it real good there. Looks like we've got another 20 seconds to go for our, let's see, that's masonite. And good. I'm glad I did all 5 of them at the same time. Different, something you wouldn't have been able to do in class here. 5 seconds. And 4, 3, 2, 1, pull. All right, let me put a little waste collector there. All right, and so masonite. That doesn't look like there's much water in there. I didn't know what to think about masonite. I didn't know if that would be high or low. But I guess we're going to find out. Like I said, that's kind of the fun of this. All right, so 229.1. 229.1 in the 300 seconds. And this then should lead us to our last one. We got about 17 seconds. 10 seconds. And we'll pull our 3, 2, 1, pull. I'll put a little collecting. I've got kind of a mess to clean up over here. But here's our last one, our pine. And we'll see how quickly we melted the ice. 192.9. 192.9. Let me double check that. Oh, really? Okay. 192.9. That's in 300 seconds. All right. So we're done collecting data. And so, like I said, you're kind of a guinea pig, and I'm going to stop real soon here, and I'm going to do the same calculations. But let me just remind you, here's the goal. Your goal is to find the thermal conductivity of it. And so their first thing is subtract these two so you can find out how much water or ice melted that became water. Then divide it by the 300 seconds so you can get the rate. Then use that in that equation over there to then do the final and main point of the lab, and that's right here. What is the thermal conductivity of these 5 materials? So hopefully that helped you a little bit with thermal conductivity, and hopefully it was kind of fun. It was for me. It was short and sweet, and well, setting it up took a long time and figuring out all the new equipment. But other than that, it was really kind of interesting, and I'm kind of excited to see what the numbers might be. But this is the lab for this week. Bye now.